This is the final update for our project, Traffic, Safety, and Incident Patterns. The motivation for our project is that vehicle transportation is a part of the daily life for most of the population. But unfortunately, in the United States alone, 38,000 people die every year in car crashes. So our motivation for developing a system is to recognize hazardous driving situations and traffic patterns to counter the human cost and the financial cost of accidents. The main factors contributing to the severe injuries and death include poor road infrastructure and management, vehicle damage or failure, unenforced traffic laws, unsafe road behavior, and inadequate post-crash care. Developing an algorithm to determine areas of danger and even predict hazardous conditions is beneficial information for traffic safety and city management. The dataset used is from the U.S. Accidents Database. It has over 4 million cases of traffic accidents covered in the 49 states of the USA from February 2016 to December 2020. Since it's a considerably large data set, we decided to use North Carolina cases exclusively. During data processing, we got rid of useless features which don't provide any useful information about the accidents themselves. Then we cleaned up the categorical features and dropped rows that had missing values in the columns. The final one hot encoded categorical features is shown on the right. We also explored the dataset and generated insights using various visualization methods. As we can see from the left two plots, the data is seriously unbalanced in different severity levels, and most of the accidents are classified as level 2 and 3. We regrouped the 4 levels into 2 levels, severe and not severe. We visualized the location of the accidents by plotting longitude and latitude of the occurrences and overlaid a North Carolina map. You can see the severe accidents versus all accidents on the plot. For our model, after the data processing, we needed to process the structured data and predict the level of severity. To determine what factors have high correlation with crash patterns or incident severity, a model must be developed that can detect and handle many attributes and weigh them to make accurate predictions. We used random forest as our baseline model since it can alleviate this overfitting effect by applying a special sampling technique called bootstrapping. Considering the dimension of the input variables, we leveraged the deep neural network to learn the associations between the features and event outcomes. We have developed an ensemble of feed-forward deep neural networks in which each network consists of 2 hidden layers, with each hidden layer having 24 and 12 neurons. In our preliminary test, we use undersampling rather than oversampling because this dataset is large enough and oversampling is very likely to cause overfitting. You can see on the right the feature importance. Given a trained classifier in a test dataset, the relationship between model predictions and true observations can be represented as a confusion matrix, as illustrated in the plots on the left. To assess the performance of each machine, we adopted 3 most commonly used performance metrics. Precision, which is the ratio of correctly predicted positive observations to the total positive observations, and high precision. We also used recall and the F1 score. From the previous figures, we can observe that random forest increases the number of correct predictions for class 0, which is not severe, and that SVM increases the number of correct predictions for class 1, which is severe. So for our future tests, we implemented a hybrid model using CNNs and LSTMs together to construct a framework consisting of 2 phases. To compare the performance of all the investigated models, we plan to randomly split the original dataset into 10 equal-sized groups to perform 10-fold cross-validation. The first function of the CNN layer is to extract the features of the power data, and the second function is to transform the one-dimensional feature data into a multi-dimensional dataset by using the output of the CNN as an input to the second phase, LSTM. The results are output through the dropout layer. As we can see from the graphs that the F1 score of our test data increased close to 0.89 over our iterations. With this, too, the accuracy starts at 0.87 and jumps to 0.9 for our testing group. Overall, the accuracy improved and started at a higher value than our baseline model did. We also had a high F1 score for both severe and not severe, solving our problem with having only high F1 scores for either not severe or severe in our baseline model. With our loss graph, we see that the training set decreases to a point of stability, with the testing set loss decreasing with a small gap under the training set, which indicates that this is a good fit and that the model has